Good afternoon. Random variable. I think that in the past classes, I have mentioned random variable is a very cute concept. So we can't using a program variable, the concept to understand here. Random variable here is what? As I mentioned, it's a kind of map. It tries to map your outcomes, experimental outcomes to real numbers. Okay. So today we will see some more formal definition. So a random variable is a function that assigns an outcome to a number. Okay. So it's a way of letting us to treat outcomes because we want what? We want those mathematical tools can be applied to those numbers. So which is reason we would like to have random variables. For example, when we flip a coin, we will get head or tail. It's hard to apply calculations, mathematical calculations to head or tail, right? But it's much easier if we map the head to 1, let's say, the tail to 0, right? So then, if we recall, in the past class, we are saying if we conduct the experiment, all the possible outcomes will form our sample space. Okay. So, and then we can associate probabilities, how likely each outcome appears. We can map those outcome, the likelihood or how likely outcome appears to a probability. So in this case, if we define this random variable, X be a mapping between the outcome of your flipping a coin to head or tail, basically to 1 or 0, then we can say, okay, the probability of X equal to 1 will be 0.5. We assume a fair coin here. So basically, you have equal chance to get head or tail. So the probability of X equal to 0 will be 0.5. The probability of X equal to 1 will be 0.5 also. Okay. So informal intuition, we can think about the random variable basically will be the horizontal value on the histogram. Why? Because we try to, if you remember, what is the horizontal bar or axis in our histogram will be those beams, right? You define those beams will be basically you define some kind of value range. In that case, informally, we actually map all our outcomes to some value range. So from that perspective, we are doing some kind of mapping here. Okay, so the random variable can be informally think as a horizontal x axis in our histogram. Any questions about the concept of random variable? So this is one of the basic elements when we to proceed with our probability. So okay. Yeah, feel free to ask questions. Even I proceed to let the slides. If you find some concept which is a conflict with what you had thought about. Okay. So again, sorry to be wordy. Just try to remember a random variable is a function that maps the outcome to a number. Yeah, just remember that definition. All right, there's two types of random variables: continuous, discrete. Okay. For example, when we flip a coin, right? So you get 0 or 1. You have two discrete cases. So this is discrete. So you can then assign the probability of how likely each outcome appears. You say X equal to 0 have 0.5 probability. X equal to 1 has 0.5. Okay, but there's another case which is continuous. Continuous is what? Is say the mapped real number is a continuous values. yeah, for example, let's say our height, okay. So if we don't quantize, say we only precise to, let's say, the 1 decimal number. If we just try to think the height is a continuous value, you are 1.4.567. Infinite number of precision. So if we're thinking that way, so this actually height becomes continuous. So then we have to handle this probability in a slightly different way. I think that we will come to this point in the next slide. Yeah. So when we map our outcomes to a real number, if this real number is continuous, then we need to handle things in slightly different way. It's no longer like a 0 or 1 to map a value or map a probability to an outcome. We need to handle it a little more careful. We will see that. Okay. So this is a histogram we have seen in our coffee shop example, right? So now imagine we start to collect infinite number of observations. Before we only counting like 100 days. Now we are counting for many more samples. Okay, and also at the same time we try to make our X bar to be as refined to as much as possible. So remember here, for example, this each bin wise will be 5, right? So now I try to make my bin wise to be as small as possible. Almost you can't tell what is it. You make things a little bit like continuous. So in that way, we are what? We are kind of, we know the underlying probability for this case is a Gaussian, right? So we are going to get some kind of very good approximation to the real probability. So this gives us an impression to say, okay, there's some probability has a distribution, looks like a bear curve, which is pretty much like what we are plotting here. Okay. So this is a very good example to say how to step from histogram to probability. Okay, so what is first, let's see one definition. What is a probability density function, PDF? Okay, so one loose definition is a histogram when the number of samples go to infinity, the bin wise approaching 0. So this is what I try to say. I hope I tell the same story. And then when that happens, so the estimate, basically your histogram approaches the the true distribution of your population. What is the population? The population is a concept I try to say is everything you want to measure. For example, all the people in Indiana. If I want to understand the distribution of the heights of people's heights in Indiana, my population will be every single people in Indiana. So that is my population. So the population will versus what? Versus the sample. Because usually I can't study the whole population. The population is usually millions of people, a very large number. So usually I'm thinking to draw a small subset from population, which consists of a sample. So if I measure every single of you, the height of you, then I will get a sample. Okay, so from the sample, what I can do is I can estimate some histogram, so which is a p hat here. But the p, the true distribution, belong to the population, which is something I could not measure or very costly to measure. So usually I don't know. So I have to get a p hat to approaching the p. All right. So I think that this concept we have discussed in the last lecture. Yeah. So however, when we try to measure our histogram, if we are able to make our sample size to be as large as possible and make our bin wise as small as possible to approaching 0, so then we get some very good approximation of this underlying distribution. So a formal definition would be the fx is a probability density function for x if the probability of this random ball stay within a range will equal to the integral of this density function. Okay, so I will give more explanations. Don't worry about it. This is a very mysterious concept to you. So first of all, before I proceed, I want to say this, what we discuss next is only valid when X is a continuous case. So if this random variable is a discrete random variable, what we discussed here is not applicable. We only, in this density function is only valid for continuous case. Okay, so this is when we talk about discrete case, we will mention something else. We call probability mass function. So that is another concept. So probability density function is only applicable for continuous random variable. All right. So this is the first thing we need to pay attention. So X is a continuous random variable. Okay. So now let's say, remember where we start. We start to say, okay, we measure histogram, and this histogram approaching a probability density function, right? So that is, if we come back to this slide, let's think about this is a infinite sample size, 0 being number, we get something about the approximated density function. So if we start from here, now this definition is try to tell you the following story. If I want to measure the probability of things happens between this or any values, any values, I will say how likely the values happens within this range. So basically you want to measure this. That will equal the area size of this gray area. If you know calculus 101, you will know how to calculate this area size. You are integrate, right, over the function. So this is the way to measure the probability of that range. So any value happens between A and B will equal to this area size. Why we care about the area size? It's because this is a continuous case. Think about our histogram. If your bin size is approaching 0, so now if I say what is the probability of, let's say A, X equal to A, what's the probability of that? Pay attention. This is a very interesting concept. What is the probability here if X equal to A, let's say, to a particular value? Anyone want to give a try? Yes. Yes, exactly. 0. Why? Because think about it in terms of limit. We are trying to make our being approaching 0. So the probability associated with a particular point in this continuous case is a super tiny, almost is 0. So anyway, in continuous random variable case, the probability of particular value is 0. What we only care about is the area, your integral over a range. All right. So this is your density. So if F, let me give a little bit explanation about the subscript here. So usually what we are trying to say here, see this is a Fx, we have a capital X as subscript. This indicates the random variable. We are talking about this density function with a target to the random variable X. And then this small x, what is a small x? This small x is a changing value because your capital X can be assigned to different values, right? So this is small x. This big capital X is mapping your outcomes to small x, to many different values along small x. I hope this doesn't confuse you. Does that make sense to you? So there's 2x in this density function. One is capital X, one is a lowercase x. The capital X is a random variable, is a mapping. In the case, this is with the interest, we are studying this density function for capital X, that random variable. Then this lowercase x is the individual values you are mapping your outcome to, right? So pay attention to there's a 2x here. Make sure you be aware. Okay, does that make sense? Please stop me if I confused you. All right, So if this is a density function, then as I mentioned, this density function will give you a curve, and then the area under the curve, this gray area, will give you the probability of the value fall between a range. So for example, if I ask you this capital X, what is the probability of this capital X take a value in the range of A and B, that will equal to your integrate this density function from A to B, basically the area size. All right. I hope everybody get the concept of it. And then the probability of each individual points will be 0. We only care about the area. All right. So I guess now you start to realize when we discuss about histogram, we are talking about 2 different ways, right? Probability ways of normalization, then another is density ways of normalization. I hope now that starts to make sense to you. When we do the density normalization, we are trying to make the area under the curve equal to 1, right? So now I hope you start to see the connection here. Recall your memory. So when we start with a raw count, right? In the histogram, each bar starts as a raw count. Then we divide the raw count by the total count. Then we say we get a probability like frequency, basically what's a fraction of the observation fall into a range. All right. Then we further divide that probability count by what? By your bin width. We say, okay, this is a density version. Then we say why we want this is because we want the area under the curve to be 1. So now that start to make sense. That means if you counting the whole area under the curve, that will give you 1, right? This is a probability because that means your all possible values will contribute, add together will give you probability equal to 1, because that is all possible cases. I hope everything start to connect it. All right. Does it make sense? I mean, if you are new to probability, this is not an easy concept. So please do ask questions. I can repeat to talk about this. Okay. So there's then after that, there's another concept called cumulative distribution function called CDF. So what we just see is called PDF, probability density function. So remember those acronym, PDF. Here we have a CDF. Okay. So what is a CDF? CDF essentially to say, if in PDF, if I pick let's say if I pick a value, if I say this is my X in PDF. So what I care is what's the probability if I have a value smaller than this given X. So that is a CDF. So how to calculate that? It's very easy, right? You are calculate the area to the left of your given point. So I give you an X, I say, what is the probability of those values smaller than X? I say, hey, everything, all the area to your left. So if I putting this area, if I putting this, counting this area into a number. So because this is area, I say this is a area, let's say equal to 0.3. Then if I plot that area to here, so every time I move let's say move to the X2, then I will counting the other area to the left. I will counting this. This looks like equal to 0.5. And I put here. So if I putting those cumulated probability with my X, then I will get a CDF. So this is what the definition here. What is a CDF? So it's a probability of when your random variable pick a value smaller than X. The X is again, this is a random variable. This is the value you are interested. The lowercase x is the value you're interested in. And pay attention here. Usually we are using f as a CDF, as a cumulated density function. Okay, sorry, cumulative distribution function. And again, this capital X is a random variable. This small lowercase x is the particular value you are calculating. Yes, questions?
Is this also only true if x is continuous?
No, yeah, the CDF is valid for both. Yeah. But the calculation will be different. For continuous one, you have to you do the integrate. For the discrete, you just summation. So, but concept is applicable. Yeah. Any questions about? Again, this is important, but probably confusing. Just remember. Think about if you have PDF, I can translate to a CDF. What I need to do is I just pick a value, then I counting what's the area to the left. Then I will get a point here, then get a point here. So you can plot your CDF. Okay. Then if this visual impression or intuition helps you, then you can start look at this function. This function tells you the value of particular x for a CDF is equal to the probability of this random variable smaller than x. So this is essentially what I try to tell in the picture. All right. Any questions about this CDF definition? Yeah, again, this is if you are new to this is not an easy concept. So please do ask questions. Or feel free to come to my office hour. I can explain more. So if everybody fine, I will proceed. Are we okay? Okay. So now we want to come to the discrete case. So as I mentioned just now, is a probability density function is a definition for continuous random variable. Continuous random variable means when you map your outcome to real number, those real number is continuous. It's not like a 1, 0, 1, 2, 3, this kind of discrete. It's continuous. Okay. But if we have discrete case, like you flip a coin, you have 0 or 1, or you roll dice, you have 0, 1, you have 1, 2, 3, 4, 5, 6. So those discrete case, we will define something called probability mass function, called PMF. So this PMF is some kind of even more close to your histogram, because in histogram, we are kind of discretize things, right? If you think about that, we try to make bins, right? When you make bins, you are discretize your cases. Even when I say, okay, the height may be a continuous value, but due to the maybe we can't measure to that precision, probably it's not true. But anyway, when we do the histogram, we actually have said, hey, my first bin is probably every 10 centimeter, I group a bin. So a kind of I discretize them. Yeah. So that make my histogram more close to a discrete case. Okay. So which is reason why we say this probability mass function is more close to a histogram. So when you have a discrete case, we can define the use this particular value. We can start to ask what's the probability when your random variable equal to a particular value. So we can start to ask this. Okay. So again, we try to see here, you have a f if you are doing the PMF. So this is a capital X is your random variable. The lowercase x is actual value. So I want to say what is the function when my capital X take a value of small x? That is equal to probability of this capital X equal to x. That means when my random variable pick a particular value. So now each individual value start to have probability. If you are continuous case, this is equal to 0. Can you see the difference there? Right? Because now I have only countably limited possible outcomes, like a 0, 1 when you when you flip a coin, right? So I can, of course, I can say what's the probability of 0 or probability of 1. If you have continuous case, each individual value does not contribute to a particular probability because they are, think about infinitely small of the bin size, almost approaching 0. So that point doesn't give you much information. Yeah, this is what we try to say here. If X is continuous random variable, any single value is actually has a 0 probability. All right. So now let's see some interesting case. I mean, this is what probability mass function looks like. You have a limited number of discrete case, like 0, 1, 2. Okay, so each of the value will be associated with a probability, and all the possible value, all the possible outcomes, they need to have a total probability of what? Of 1. So for example, here you have 0.5, 0.25, 0.25. When you add up together, this should be give you a 1 because you are distribute the total 1 probability over all possible outcomes here. So when you add them together, they need to be 1. Okay. The same thing happens, as I mentioned, for density function. This is a probability of density function. Okay. For information, this is a one very famous distribution. This is called what? Called uniform distribution. All right. This is a. If I tell you this is a density function, a probability density function, what you can tell here? What you can tell from this figure? This is some PDF. So first of all, X is continuous. Then second, what is most important? Why it is called uniform? Does somebody see that? Yes. Yes.
The probability of any given value is the same.
Exactly. So any value, first of all, any value smaller than A has a 0. Right? That is fine. Anything above B equal to 0. Then anything between A and B. So that means if my random variable, anything happen in between, they are kind of uniformly distributed, right? Because they all share the same value here, right? So then if I ask you what is a CDF here? What is a cumulative distribution here for this guy? Should be very easy. Actually, it's very, think about that. Give yourself maybe 10 seconds to think about what is a CDF here for this guy. Yes.
Is it X minus A over B minus A?
Yeah. So
If like X is a value between A and B.
Yes. So if I A, B, and you can teach me how to draw it. So the first point, what the point at A? If I draw it, what should I corresponding to 0, right?
Yeah.
Then what is the points I should corresponding to B? So yes, exactly 1. So if I draw a CDF here, then because when I move from A to B, my probability will increase linearly, right? I think that this gentleman said the right also answer. So this is 1, this is 0. So this will be some kind of CDF. So basically everything before A, you have 0. Everything after B, you have 1. So then between things between A and B, you are linearly increased. So this is a CDF function for a uniform distribution. All right. I hope when you see these 2 examples, this guy and this guy, you start to get a little bit understanding from this trivial case. All right. Are we fine about this PDF and CDF here? Yeah, please do stop me if there any concept here which confuse you. Are we fine? Are we good? Yeah. So then there's another concept I haven't talked about that. There's a possible try to define your density function from the cumulative distribution function. Because you can always think your density function is a derivative of your cumulative function. Because why? The reason is that if you come back to see this picture, we are trying to integrate over the area, then reporting that value as my cumulative value. So from that perspective, from the calculus concept, we know we can take a directive to go the reverse. So here, for example, if you look at this picture, what is the directive of a straight line? It's its slope, right? Because I have a straight line, so my slope is constant. So I can, so for here, of course, you have 0, but for here, you have a constant slope. So which is reason you will have a constant line. So which give you some intuition why this is true. All right. Any question about this? Yes.
Can you explain the first graph, like the one on top?
This guy.
Yeah, what is that showing?
Okay, this is trying to show a discrete case. So basically, when I do my experiment, there's only 3 possible outcomes. Okay, so your outcome space will be 0, 1, 2, only 3 values. So then you are mapping your each individual outcomes to a probability. So I would say this guy with 0.5, this, sorry, 0.25, this is 2.5, this guy. So this is a PMF. This is a, try to explain this equation. Yes, questions? Yes, if you, because remember, we have a omega, right? This omega contains all possible outcomes. So if that says your all possible outcomes, of course, they should need to cover all possibilities, right? So then the probability will be add up to 1. Questions? Okay. Anyway, it's also a good chance for people who already know this to review your understanding about those basic probability definitions. Those things are the, how to say, some very essential or basic concept in order to proceed. All right, so what do we have learned? The probability density function, probability mass function, cumulative distribution function. When I say the name, try to recall what's the definition of those. Better remember them in terms of some picture, some curves. All right. So now we will talk about another very interesting concept called how can we estimate your CDF from data. Okay. So let's first talk about the definition of CDF. Of course, we have already seen that, but now we want to put everything into one slide. Okay. So the CDF for continuous case is try to say, okay, remember this is a general definition to say, what is a CDF? The CDF is the probability you give me a x, a lowercase x. I will say the CDF measures what's the probability of my values to be smaller than given small x. So, all right. So this is a definition. It's applicable to both continuous and discrete case. But if we are talking about continuous case, we will say this probability will equal to from infinity, negative infinity to the x. That essentially to say, if I do the integration from negative infinity to x, right? So this is a think about this is an area to the left of your x, if you are given a density function, given a PDF. Any questions? Okay. So if you have a discrete case, essentially the first half is the same, but the only difference is now you are trying to replace your integral with a summation, because now you no longer have this density function, you have the mass function, the probability mass function. So now you have those individual discrete cases, you will add them. So, but essentially this two is just one is a continuous form of the other. Okay. So basically you are adding everything, adding all cases to your left, essentially. For example, if I say what's if my x is a pick a value of 2, I will try to adding the 1 case, 0 case. I will adding individual probability in order to count the cumulative distribution function. All right. Are we fine? So now we will come to the most interesting part. I think that this is a so this is a discrete empirical CDF. So pay attention. I think that this is probably a very is a very easy concept, but if you didn't get it, then it can be a very confusing to you. So if I give you a bunch of data, let's say I give you, this will be the data I give you, negative 1.5, 0, 0.6, 0.7, 1.3. I give you a few numbers. I ask you, hey, using this number to plot a CDF for me. Okay, so this will be the task. All right. So what to do? How we can plot a CDF from these 5 or 6 numbers? There's a few things to remember. First, we try to say each of the values here, we'll try to contribute 1/n probability. So if I have n sample or n observed values here, so here basically is a n equal to 5 in this case, right? If I have 5 values, each single value will contribute 1/5 probability. So this is the first thing. And the second is we need to sort those values from small to large, and then start to count, and then add accordingly. So this is a general procedure, and we will see how this proceed. Okay. So first we will try to sort our values. These values already sorted very good. Then we will start to move from small to large, and start to adding. Each value will contribute additional 1/n to me. Okay, let's see what happens. So I will start from this first guy, negative 1.5. So initially I start from here, nothing, because I never see any observation. until I see negative 1.5. Then I will adding 1 over n, which is 1. We have 1, 2, 3, 4, 5. So 1 over n equal to 1 over 5, and equal to 0.2. So I will put a 0.2 here. If you measure here, this is a 0.2, this guy. Okay. Then I will keep moving to my next guy, which is a 0. So I will keep moving because there's no observation. So my probability or CDF function doesn't change. So I will moving until I reach 0, reach this guy. I have next observation happens. So then I will try to adding another 0.2, right? So I will get 0.4 here, right? So then I keep moving. My next value will be 0.6. So I keep no change for the remaining value until I reach 0.6. I will adding another 0.2. Okay. Until like the last value will be 1.3. 1.3 here, it will complete the last adding, will make your CDF value reach 1. Then no more change. Because the maximum value you can have for CDF is 1. Right? Does this procedure get it? Did you get this procedure? So basically what the first part again is the same thing as before. But now what you try to do is more like a discrete case. You want to adding the probability associated with each individual observation. And in this case, we will try to make 1 over n as a probability. So does this procedure make sense to you? I give you a bunch of points. Let's say I give you 10 points. Your first thing you need to do, you sort them from small to largest. And you remember each value will give you 1 over n, because this is you only have 10 possible. So that is your whole world. You only know these 10 numbers. So of course, each value will give you 1 over 10, like 0.1. So then you will start to say, hey, what is the smallest number? Anything smaller than that, because you have no support, you have no observation. So that, of course, that will associate with the probability 0. So then you see the first small number, you say, hey, I see this guy gave me some things. I will increase my probability by 0.1. Then I move to the next guy, the next value, say, hey, if I see this, then I will adding a little more support. So I will, that the second guy will contribute another 0.1. Then you move your CDF a little bit up. So at the end, you will have something like this. This is your empirical CDF, empirical cumulative distribution. Are we fine with this empirical concept? Because this is closely related to the next concept we call QQ plot. Yes, questions? I think we have something related to this. We have some, which is the next slide. Sorry, we will have something like this guy is actually using this concept. Yeah. So anyway, this is an important concept. I hope you make sure you understand how to do this. Possible. Yeah. This is all this is possible. Yeah. This is a very important procedure. I'm not say super important, but it's good for you to know since you are playing with data science. Do you want me to explain a little bit more about this? Are you fine with the procedure? How to plot this? Are you okay? Okay. Yeah, this is very useful because if you in real world you see a lot of data, right? The first thing you want to say is what distribution is this data? You actually have no way you just stare at those numbers, but this gives you a very effective way to have to come out with a CDF. Then you can start to decide what distribution inside of it. Right? This is give you one of the very important way. Okay, so this is actually the next topic we are talking. So how to pick a distribution. I give you a bunch of data, then you say, hey, this is a Gaussian, this is a exponential distribution. What exactly is that? We need to have a way to draw a conclusion, right? So because once you really have a very good approximation to say what is distribution, then you start to get you can estimate the number, the parameters. You have a lot of more interesting you can do. Yeah. Okay. So, but how to do that? How to determine what distribution you have within your data? So what we just see that is empirical CDF give you a very neat way to do this. But we will not directly use that, but instead we are using something we call QQ plot, quantile plot. Okay, but the basic idea is the same thing. You compare the CDF of your data to the CDF of your proposed model. So basically, you have a bunch of data. You are using the way we just see to estimate what's the empirical CDF, and then you will try to see, hey, this is I predict or hypothesis this distribution is a Gaussian. Then I will try to compare your proposed model distribution with my empirical distribution to see does they match. Okay, so the basic idea is here. But we are trying to using something we call quantile to perform this procedure. What is a quantile? The quantile Q is a value of X such that Px smaller than X equal to Q. So basically, the quantile, if I give you a quantile, if I give you a value Q, then you tell me, think about this. I think it's better to tell from the figure. So what is trying to say? I will ask you if I want all the area under the curve to equal to Q, what is the corresponding X? What is the value of this guy? So this is what quantile try to ask. So if you see the definition, I have P X, capital X smaller than X equal to Q. So basically what this guy, this is an area to your left of this X. And if I make this guy equal to Q, and the quantile is a value of X to achieve that. So first of all, quantile is a value of X. So this guy is your quantile, but that will give you the area on the curve equal to Q. So what is that? Mathematically, what is quantile? Mathematically, quantile, is anyone want to give a try? What is mathematically, what is quantile? Quantile is this a inverse function of a CDF, right? In CDF, I give you an X, you are calculate. The point to that X is the area to your left, right? But now I tell you, if the area to my left equal to Q, what is U, right? That is an inverse function. All right, does that make sense? So I think that the more friendly version of the quantile is a percentile. So I think that if you take the test, you always know that, right? So what is let's say you are scoring in 95 percentile on a test. What does that mean? That means you achieved a score, and the people who smaller than your score contains 95 of the under the area. So probably you are here, right? So this is your score. You achieved 95. So this area equal to 0.95. Right. I hope this make you a little bit more clear about. So Yeah, probably I left. I think that maybe I stop here. Maybe I will start from resume from this place.